Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you learn how to write equations to describe the displacement of objects. And when you're studying the motion of an object, the first thing you do is you put a coordinate system in the problem. So we're going to talk about this coordinate system right here. Now, logical places to put a coordinate system, well, this would be a pretty logical place, so that at t equals 0, the x-coordinate of the car is 0. If I put the coordinate system over here at t equals 0, the x-coordinate of the car would be some negative number. Over here, it's some positive number. Now, again, the orientation of the coordinate system also is a factor. There is nothing wrong with a coordinate system that looks like, like this, right? And right now, at t equals 0, x would be some negative number. And here it would be 0, and here it would be some positive number. You can orient a coordinate system any way you want. I'm going to go ahead and put it back into a more, I guess, standard looking form here and just leave it right here. Now, with the location I've put this coordinate system now, we now have an initial x value, and that is this distance right here to the red dot. So that's what I would call, an x initial. That is some positive number in our problem now, right? And I'm going to talk about these three cases here, just like I did in my previous example. Case 1, the velocity is to the right and the acceleration is 0. So this car is just moving along at 20 meters per second or something, and that velocity not changing. And what would happen then is your x-coordinate would get bigger and bigger and bigger. Now, I already talked about how to write a velocity function for this, right? Your velocity graph would look something like this. This graph would be horizontal because the velocity is not changing. And again, you graph it out to what I just call kind of an arbitrary time t. The equation that describes that velocity would be v of t equals some number. I just called it v sub o in this problem. That would be whatever the velocity of the car is. Positive if the car is moving this way, negative if it's moving this way. All right, now, the displacements. So hopefully you've seen my video on how to do this. Your delta x, right? Once you have a velocity graph, the delta x's are calculated by the area under the curve here. That area right there will give the delta x, because the delta x is velocity times time. I'll go ahead and put this in red, so that's equal to v initial t. The v initial is whatever this distance is, the t is this distance on the graph. Now keep in mind that the delta x is equal to x final minus x initial. Whoops. And this is always, always, always true. And then to get our position function, we just move the x about to the right. And I'll go ahead and look at numerical examples of this in my next video. And this x right here is a function. X of t would be a good thing to call that, because it's time dependent. You'll notice it's got a time right there. And it's linear. All right, let's take a look at case 2, where the velocity and the acceleration are in the same direction. And I had intended that to both be right in this example. So cars moving to the right at, 6 meters per second to make up a number, and accelerating at 2 meters per second, something like that. Then the graph, right, would be linear, and it would look something like this. I went over that in my video about how to write velocity equations. Your velocity function will be some linear function. We've already done that. All right, the new step now. So the delta x, right, just like the previous example, you get from this area right there. And this distance on the graph is v sub o, presumably some number. And here's the part that seems to give people a lot of trouble. This distance on the graph, right, is a function, because it's time dependent. The further right you go, the longer that red line is. It's equal to v of t. which we found right here. That's what this is. Now, this geometry is a trapezoid. So if you're not familiar with finding the area of a trapezoid, I've got a video on that. Just go back and take a look. This is how I do it. Left plus right, divide by 2 times the width, right? So that's going to be, the left is what we're calling v sub o. The right is this distance, which is described by this function. At plus v sub o over 2 times the width. The width is that distance. That's what we're calling t. And it's not too hard to show that when you clean this up a little bit. You get v sub o plus v sub o over 2 is v sub o times t. And then you get, by the time you do this times this over this, you get plus 1/2 at squared for any given acceleration. And just like over here, just like on the left, this is equal to x minus x sub o. So by time you, add x sub o to the right, you get this. You'll get some sort of quadratic. Case 3. Case 3 is really identical to case 2. I'll call it case 2.5. In case 3, the only difference is, right, in this equation, you're going to end up with a negative number right there and then a negative number right there. But how you work the problem is identically the same. So anyway, that's how you develop equations of motion for either zero accelerations or constant accelerations. I hope that this helps. Have a great day.